right, go and take out your textbooks. Turn to page 473. Page 473, going to look at the homework that we had in our last lesson. We were reviewing over chapters 8 and 9 in our last lesson, lesson 136. And today, going to go over chapter 6 here in just a moment, but want to start by doing one last quick look here. Numbers 9 through 14 and 17 through 24 on page 473. All right, there's the 9 through 14. There's the 17 through 24. Bueno. All right, number 9. What is the sum of all the probabilities of all outcomes in a sample space, Lana?
I just put event. I didn't.
An event is a particular desired outcome, but what if you had lots of different outcomes that could happen? If you added them all together, you would get, Josh? 1. The sum of all probabilities in a given situation is 1.
That one always goes.
All right, number 10. What is the name for a product of factors in which each factor is 1 less than the previous and the last factor is 1? Lana?
Factorial.
Factorial. Number 11. What are events in which the occurrence of one event does not influence the probability of the other event's occurrence? Joshua? Independent. Do you see the difference between independent and mutually exclusive? Mutually exclusive, you cannot have the two exist at the same time. Independent means the first one doesn't necessarily affect the other one. They could both happen, it's just the one doesn't mess up the other. Number 12, what's the middle value in a ranked list of data? Lana? Media. Number 13, what's the ratio of the frequency of an outcome to the total number of outcomes? Total relative frequency, right? So how frequently something happens. For instance, if Glenn gets 8 hits in 12 at-bats. Well, that's a relative frequency of, what would that be, 6.667, 667 batting average. That's pretty good, right, Glenn? You take a batting average like that in baseball, right? 8 out of 12. Anyway, total number of outcomes, you went up to bat 12 times, got to hit in 8 of them. Now again, strict theoretical probability, he either will or won't get a hit, right? 50%. Based on past occurrences, based on observation, based on experimentation, if you will, the experimental probability, 8 to 12, which would be a relative frequency. Number 14, what type of graph is the visual representation of a 5-number summary? Lana? And we actually see one of those down there, number 23, a box and whisker plot. Number 17, each of the 10 letters in the word bookkeeper, by the way, it's the only word in the English language that has 3 double letters in a row. O-O-K-K-E-E. Right, in a row. Anyway, that's cool. But each of the 10 letters in the word bookkeeper is placed in a jar. What's the probability of randomly drawing an E, Lana? 3 to 10. Number 18. What? Okay, there are 3 E's out of 10 total letters in the word bookkeeper, so 3 to 10 probability. Question on that? What did you have?
I had 1 to 5.
Oh,
because you said there are 5 distinct letters. And one of which is E. No. Now, not each of the 10 letters. There's actually 10 in the jar. Number 18. What's the probability of choosing a letter that is not a vowel, Joshua?
1 to 2.
1 to 2. There are 5 non-vowels. B, K, K, P, and R out of 10. What's the probability of a K or a P, Lana?
3 to 10.
3 to 10. 2 Ks, 1 P. Because again, or you would add those together. 2 to 10 plus 1 to 10 is 3 to 10. What about a vowel or a B, Joshua?
3 to 5.
3 to 5. There are 5 vowels. There is 1 B. That's 5 to 10 plus 1 to 10 is 6 to 10, which reduces to 3 to 5. What about the probability of an R, replacing it, and then drawing an E, Lana?
3 to 100.
3 to 100. Okay, so this is and, so we're going to multiply these. And R, well, there's only one of those, so that's 1 to 10. You put it back, so there's still 10 there, drawing an E, that's 3 to 10, but you multiply the 1 to 10 times 3 to 10 to get 3 to 100. Number 22, an O, not replacing it, and then drawing the other O. Joshua.
Oh, I think I messed up, but I got 1 to 50, but I don't think that's right.
Yeah, how many O's are there?
2
Out of
10,
the first time. But if you don't put the O back, how many O's are there?
9.
Well, there's 9 total, of which one of them is an O.
Yeah.
So, yeah, should have gotten 2 to 90, which would reduce to
1 to 45.
1 to 45. 1 to 45 probability. What about the probability of a vowel or let's say, the probability of a vowel or one of the first 5 letters of the alphabet. Drawing a vowel or drawing one of the first 5 letters of the alphabet. Well, how many vowels are in the word bookkeeper?
5.
Out of
10.
10. Or means we're going to add. Now, what are the first 5 letters of the alphabet, class?
A, B, C, D, E.
All right, how many A's, B's, C's, D's, or E's are in that word? 4. There's a B and 3 E's. There's 4 total letters that would fall in the first 5 letters of the alphabet. Now, are there any of the first 5 letters that are also vowels? Or you could say, are there any vowels that are also first 5 letters of the alphabet?
Yes.
How many?
3.
The 3 E's, right? So because there's that overlap, remember, we would have to subtract that away, wouldn't we? And what would be the probability then of a vowel or one of the first 5 letters? 6 to 10, which reduces to 3 to 5. Questions on a not mutually exclusive example. Again, the book doesn't generally provide those since it was a level up, but I want you to know that, so practicing there. Number 23, they give you a box and whisker plot, and pretty wide dispersed data. There's actually 2 small regions where much of the data is concentrated. A lot of the data is between that lowest value called class the minimum and that median of the first half, the lower half, called the first quartile, right? There's a lot of data in there because it's really small. There's also a lot of data between the
First quartile.
Median and the third quartile, right? Because again, it's a small section. So where the section's small means there's a lot of data packed into a small space. Where it's bigger, that means there's that same amount of data, but it's over a wider space. Because there's the same amount of data in each portion. So if it's small, that means there's a lot of data in a little region. But anyway, what is the 5-number summary for the box and whisker plot? Joshua? Number 23?
30.
Did you forget to do it?
I forgot to do that one.
All right, doing it now. You said 30 is your minimum.
30, 34, 52, 58, and 71.
Good. 30 minimum, 34 Q1, 52 median, 58 Q3, and 71 max. Did you have that, Lana? All right, number 24. What is that thing we got going on there, that red, white, light, weight times thing, class?
7.
What is that thing? It's called a... What type of graph is it?
Oh, stem plot.
Stem and leaf plot. Stem and leaf plot. Did you?
Yeah.
I didn't hear you. I'm sorry. I'm deaf. Stem. I thought you said 75. I'm like, I don't know where she got 75 from, but I don't know what answer she's trying to give me here. Stem and leaf plot. I'm deaf. Sorry. All right. All right. So a driver recorded how many minutes he waited at red lights each day. Which class has only 2 data values in it, class? The 0 class, right? Which class has only 1 data value?
The 30.
The 30s class. Yeah, the 30s class. There was only 1 day he waited in the 30-minute range. Obviously, how many days was that longest wait, class?
19. Oh wait, 32 minutes.
32 minutes was his longest wait, right? But anyway, let's go and take a look here with the 2 data values, zeros. How many days did he wait at least, at least 20 minutes, class?
5.
I put
5.
Why did I?
He waited exactly 20 minutes twice. He waited at least 20 minutes 5 times. He waited 20, 20, 23, 24, and 32. Gotcha again. What was the shortest wait he ever had at red lights for a trip?
8 minutes.
8 minutes was the shortest. I'm guessing combined red lights, because it says red lights, not a single red light.
Wait, 8 minutes at a red light?
At red lights. So that means, let's say he has like 7 red lights on the way to work, and he ended up waiting like a minute at each one or so. 8 minutes total versus like he has 7 red lights, and he ends up sitting there for a total of 32 minutes at light. So just kind of keeping a running tally for the trip. Probably it's more than 7 lights. Probably, I don't know, 10 or 11 red lights. Anyway, I digress. What was his shortest wait? We said 8 minutes. Are there outliers?
Yes.
I would say no, because there's not a gap in the data, but there kind of is, right? I mean, 32 minutes, Lana. How far is that from the nearest data value? 8 away, right? 24 was the next closest. Well, there's never a gap that big anywhere else, right? 8, 9, 11, that's a gap of 2, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, there's a gap of 3, 24 is a gap of 1. The biggest gap has been a gap of 3. And then you spring a gap of 8 to go from 24 to 32. I can see why they say yes. I think technically one might argue yes. I'm also kind of where Joshua's at, like, there's not like an enormous gap. I
Can you
mean,
put that like on a quiz or test and kind of
it would be more obvious on a quiz or test.
Yeah.
It would be more obvious. I wouldn't give you, because that one's right in between a yes and a no, where I could see both sides. I would make it really obvious. Either there's a definite yes or a definite no. For instance, if there'd also been a 33, there's now no outlier. Or if that had been, say it had been a 29 and a 32, like if there had been a 2 with a 9 as a leaf, there would obviously be no outlier, because a gap of only 3 is not an outlier. Again, that gap is 8. I think there probably is an outlier there, but it's not an obvious outlier based on the arrangement of the stem and leaf plot. What's the mode of the data, Joshua? 17 minutes. Okay, Lonnie, here we go. What's the median of the data?
I got 5.5.
What?
5.5.
I cannot find
All right, what's the median, Lonnie? It's the
middle.
value, right? So we have 0, 1, 2, 3. We've got 8, 9. We have 1, 2, 3, 3, 4, 5, 5, 6, 6, 7, 7, 7, 8, 9. 0, 0, 3, 4, 2. All right, so I'm going to do it the lazy person way. You ready? 1, 1. 2, 2. I got a long way to go, don't I? I'm going to cross out 3 here, 3 here. I'm going to cross out 3 here, 3 here, 2 here, 2 here. That's the middle.
Well, at least I was close. I put 5.5.
Should be 16.
Okay.
Oh. It showed like 15.
Oh, I see. You were picturing it falling here. You were just a couple.
Yeah.
Okay, 15 and a half. Careful. Yeah, that one is important. So 16 minutes would be his median weight. But does that make sense? How we can, instead of doing 1, 1, 2, 2, 3, 3, 4, 4, like one at a timing, you can cross out clusters at a time, as long as you cross off the lowest cluster with the highest cluster, lowest cluster, highest cluster, and so forth, right? So you can cross off clusters of them and save yourself some time as well. But 16 minutes was the median there. Most days he ends up waiting somewhere in the tens minutes range, right? Somewhere in the teens. A teens minutes is pretty normal for him. So most days he's under 20 minutes of wait time at red lights. Now again, that's not travel time because there's a driving as well. It just says just waiting at red lights. Questions on
But
this?
the mode was
The mode was 17 minutes, yes. All right, any questions on that? All right. Go and set your, not set the book aside, but turn back, if you would, to page number, I'm going to set my book aside because I have 2 volumes. Back to page 232. 232. I just want to skim through chapter number 6 and refresh your memory on some things, and then we will drill over some long-lost area formulas. Now, hopefully, over the weekend, you spent some time studying area formulas and just refreshing your memory. How many spent time studying?
well, like
How many
today,
did not spend time studying?
I know, I spent
A little
time
bit.
today.
Oh, today, okay. All right, earlier today studying, just getting ready for this, okay, since we had study hall just before this. All right, well, let's go ahead and look at this. Remember area, it's how much stuff is enclosed within a plane figure. What would be that which is contained within a solid figure?
Wait.
Contained within a plane figure's area, contained within a solid figure is called
surfaces.
volume.
Yeah.
And what is contained within the surfaces of a solid figure? That would be surface area, right? So it's also important to remember area and surface area and lateral surface area is measured in what kind of units? Square units. While perimeter, individual lengths are measured in just plain old units, and volume is in cubic units. Okay, so some little things to remember there. The area of a square, A equals S squared. I think we got that one. Should remember that one pretty well. Parallelogram, remember you got the A equals BH there. That's the same as a rectangle. BH or sometimes LW. Don't throw it in your eye, Glenn. Triangle. Triangle, A equals a half BH. Scott, you miss all of this. Triangle, A equals a half BH. Hey, at least he's like, my eyes are protected because he can't throw that paper airplane through this computer screen at me. Glenn might find a way, I don't know. All right, anyway. Triangle. You see there the 1/2 BH. Okay, so remember that's half of a parallelogram. And then the trapezoid's the funny one because it has two different lengths of bases. So just remember, it looks kind of funny. The 1/2 H times B1 plus B2. In addition to just using those area formulas, though, you see that picture there of the triangle on a grid, right, where we were able to say, okay, well, let's see, count them. 1, 2, 3, 4, 5 is the base, but it's really 15. And 1, 2, 3, 4 is the height, but it's really 20. And, that's 3. That's 4. So we would get the height, but it's really 3, so 12. And you do all that funny stuff. You remember doing that? Go ahead. Do we want to work one of those picture thingy sketches just for practice sake? That's kind of what we're doing, is what do we feel uncomfortable with versus we feel strong? That's something we want to work one of those?
Yeah.
All right, let's go ahead and do one of those real quick. Make sure we're good to go here. All right, so let's suppose, okay, let's do this. We have to zoom in for Scott just a little bit here. And let's suppose, all right, so one box has 2 inches on a side. Zoom in a little bit there for you, Scott. What's the area of the triangle? Well, we're going to start with the formula, right? What's the formula for the area of a triangle?
1/2
Half BH. So we need to ask ourselves, what's the B?
16.
Good. It's a total of 8 units, right? Starting here at 0, 1, 2, 3, 4, 5, 6, 7, 8. But it's 2, so 16 inches. And then the height, starting at the base going up.
5, 6.
But it's really
12.
12 inches. And then do you remember the shortcut we mentioned here?
Take a
Just
half
half of-
Half one of them. I would take half of the bigger one, which is 16, to get really, it's 8 times 12
96.
inches squared. Lana, feel a little bit more comfortable with that? Okay. Now, as you turn the page, we also looked at complex figures, where instead of just a straightforward area formula turning the page, we had to break a figure down into 2 other areas. Okay, and this was fun, right? Drawing those auxiliary lines, those dotted lines to break things down, so that if I had a funny looking figure here, and I said that, I don't know, this line here is, let's just say 20 units, and this line here is 8 units, and this line here is 9 units, and this line here is, let's say, 15 units. If we wanted to find the area of the figure, what would we need to do? Well, that's a weird figure. We don't know how to find the area without drawing at least one auxiliary line, Lana.
Like down the middle of it.
Like you're talking about right down here?
Yeah.
I'm just gonna do that.
All right. Well, there's actually a number of ways you could do this, Joshua.
Yeah,
you could draw a line right there as well. There's nothing wrong with Lana's line, because Lana, we know this line has to be how long?
9.
9. And we know this piece has to be how long?
Wait, 8.
8.
Yeah.
Which means this piece has to be how long? 7. Because this whole thing is 15. If 8 is there, that only leaves 7 units there. And now all of a sudden you could look at this as a trapezoid and a rectangle, couldn't you? What would be the area of the rectangle? That's the easy part. Base times height?
72.
72 square units. Now the trapezoid we have to look at kind of sideways, don't we? What's the formula for the area of the trapezoid again?
1/2 H parentheses B1.
Oh,
Now, what are the two bases of this trapezoid?
the bottom one right there, and then that one.
Right, so add them together, we would get a sum of 29. What's the altitude or the height of the trapezoid? That's the 7, right? That's the height of the trapezoid. So we take half of 7 times 29, and this is just obnoxious, isn't it?
Yeah.
Well, here we go, 7 times 29. Let's just cut it in half when we get done. 7 times 29. Hayden?
203.
Wait.
Yes, sorry, 203. 203, and then we gotta cut that in half, right? So what is half of 203? All right, 101.5 or 101.5. And so we take this region and that region, add them together, we get 173.5 square units. Right, 101.5 here, 72 there, adds up to 173.5. You could have also done it Joshua's way. Which Joshua's way was to cut this across and say that this piece here was 9. This piece here then, Joshua, was
8. Wait. What? Oh.
This was your method. I'm just going with what you said you were going to do.
Long was over, so I was getting clear. But,
So if this piece is 9, then that piece has to be
no. Oh, 11.
11, because the whole side here is 20. So we just subtract the 9 off. Now it doesn't look like 11. We can't trust our artists, not drawing a scale. And then furthermore, the only hard part is, what is the height? If you call this the height, what's the base of just the triangle, right? So that's where we still had to draw Lana's line, and we actually ended up breaking it into 3 pieces to do it your way.
Yeah.
That's one of the upsides, I would say, to just drawing the trapezoid line and rolling from there. But it would have worked out to the same answer. Questions on complex figures? Again, you're using those area formulas. We also might have an area problem where you've got, maybe a square, and each side is, say, 10 inches. But within the square, we've got a rectangle that's been cut out.
Oh.
And maybe this had a side of 3 inches and a side of 5 inches. What's the area of the unshaded portion? Well, what would we have to do?
I got it.
15.
Well, that's the area of the shaded portion,
Yeah.
right?
Yeah.
This here is 15.
And then.
But what's the area of the unshaded?
40?
100.
Well, the whole area is 100, right?
100.
So what's the area?
90? Wait, no. 85.
85 square units.
You just
Oh,
subtract the whole.
You subtract the shaded from the whole to leave you with how much is unshaded. For instance, if this were a window in a room, then, which that'd be kind of a weird wall, anyway, but if it were, then you would simply subtract that area away to see how much would have to be painted, for instance. Now we can also, as we turn the page, a couple of times, there we go, we can get into circles, right? And lots of terms about circles, right? That line from the center to any point on the circle, radius, a line that goes from one side to the other side of a circle, just a chord. Now if it goes through the center from one side to the other, now it's a diameter. Diameter goes through the center, chord doesn't necessarily. Now if you really wanted complete side to complete side, you're right, Joshua. To measure how wide all the way across, it would be a diameter. So maybe it was a misleading question. From one end on the circle, the other end on the circle, that's chord. But technically, I guess you'd actually be right. They're side to side. But anyway, a portion of a circle, of course, called an arc. An angle, there you see central angle. Angle formed by the 2 radii with the vertex there at the center. Semicircle, half the circle. Sector of a circle. bounded by an arc and the 2 radii, like a pizza slice. Circumference formula, C equals 2 pi r, or pi times d, since a diameter is simply 2 radii, right? So really the same formula, it's just another way of looking at it. Where pi, remember, has 2 values we could use. We might use
3.14
or
22.
Yeah.
right, and if we really only want to use this if we've got some number in the problem, like a radius or diameter that has a 7 in it, like a 7, 14, 21, 28, 35, 42, 49, or so forth, right? A multiple of 7. This might be helpful. Pi Day yesterday. Scott, if you're watching this on Ides of March, like I hope you are. But anyway, Pi Day yesterday, 314. So. What? Ides of March. That's the middle of March. I'll ask Mrs. Henderson about the Ides of March. It's a very famous day. Julius Caesar was brutally murdered by a friend, literally stabbed in the back by the members of the Roman Senate on the Ides of March, and he'd been warned by one of those, fortune teller people called a soothsayer. Beware the Ides of March, beware the Ides of March. And he ignored him. He's like, get away from me. Dead. Just realized, Scott, I was kind of running you out of room there on the chalkboard. But anyway, that's neither here nor there. 3.14 or 22/7 is what we use for pi. Area of a circle. Of course, we remember, class, that.
Pi r squared. Yeah.
Pi r squared. But is pi really squared? No. Pi r round, the box the pi comes in, r squared. You see that?
Yeah.
Yeah. Round pi and square box, it's true. Anyway. I digress. So anyway, practice with finding area of circles and stuff like that. I feel like we're probably good with that. I guess the one thing might be this. If we had, for instance, a circle.
Oh, that's like really perfect.
And if I had a rectangle, and let's suppose I knew that this diameter here, this line, let's call this line AB for sake of reference here. AB was, let's just say, at 10 inches. And let's suppose for a moment that this line here was 8 inches, and this line here was 6 inches. And I wanted to find the area of the shaded portion of my circle. Talk to me. What would we have to do to find the area of the shaded portion?
8 equals pi r squared. 3.145.
8 squared.
Well, what's the radius?
Oh, 6.
10.
That's the diameter.
Oh, 5. Right? 5 squared.
Given the diameter, you know the radius is going to be half of it, so each radius is going to be 5. So the area of the entire circle is pi r squared, which, find it real quick. Yeah, 78.5, approximately, I guess I should say approximately 78.5 inches squared. So that's the area of the entire thing, right? But if I only want the shaded region area, I would have to do what? Take out the rectangle, right? And what is the rectangle's area?
48.
Right, 48. So we're going to subtract the whole from the whole. Right? The entire circle minus the hole that's being cut out of it, so minus the 48 inches squared, gives me approximately what area shaded in?
30.5.
30.5 inches squared. Questions on that? Okay. It's the same thing we did here. We took the area of the WHOLE minus the area of the HOLE, and we're left with the area there in unshaded territory. We can do them circles as I pointed out there. Lots of stuff on these other pages. Three-dimensional figures. Polyhedron. A polyhedron, plural polyhedra, right? Flat faces everywhere, right? Like a box. But we said you could also have a just a continuous cross section because you have congruent parallel bases at the ends. That gives you what we call a, you can look at the page and sheet, prism, right? Congruent parallel bases on either end would form a prism. Now, what the other faces are, who knows, right? For instance, if it's an octagon on one end and an octagon on the other, you're going to have 8 other faces going around, right? But the ends are still, if they're congruent octagons, well, it's an octagonal prism, right? You could have squares, triangles, you have all kinds of different shapes there for your prisms. Now, if you have just one base and it goes to a point after that, that's called a
triangle thing.
pyramid. A pyramid. Pyramid has a flat base and goes to a point at the top. Now, that assumes we're talking about a polyhedron, correct? Where you have flat faces. For instance, if you had a circular base, you just have one continuous wraparound coming to a point. That wouldn't be a pyramid, that would be a cone. A wraparound coming to a point would be a cone. She's not good at visualizing these. She needs it on paper there. But anyway, so prisms, pyramids, of course, curved figures. We had the sphere, which is a ball, right? We had the cylinder, which has like a prism and that has congruent parallel bases. But again, it's not flat faces going around like a prism. It's just a full wraparound with 2 parallel bases that are both circles. That's cylinder, right? The cone, one circular base comes to a point, and then the donut, which we call a torus. See, we remember that one. Great. Speaking of which, Golden Donut's still not opened.
Oh, I didn't even know that.
But Lord willing, going to reopen sometime in the next month or so. Okay, so they've been down and out, which is why there have been no donuts on this campus in a very long time. Well, there have been donut holes. Miss Morse brought some donut holes, Scott, in celebration of making it longer this year than we did last year. Since last year, we didn't make it to the first day of, actually, it's not even technically the 4th quarter yet, but we didn't make it this far last year. 3:13 was our last day. Anyway, you see all those prisms and pyramids and 3-dimensional curves. We're not going to get into nets of polyhedra on the exam, so you don't have to worry about those nets and stuff. Let's see here. Surface area. Formulas. Here we go. Page 254 is where we're at now, as we're kind of flipping through here. Surface area. Remember, that's the area of all the surfaces? The area of all the faces of a polyhedron, or any 3-dimensional figure for that matter. That wouldn't have faces if it wasn't a polyhedron. So anyway, but yeah, so the rectangular prism, you note that the 2LW plus 2WH plus 2LH, the cube 6E squared. Remember, lateral surface area ignores the top and bottom, only looks at the sides or the lateral parts. Bottom would be beneath, top would be above, laterals, that which is around, surrounding you. But that would be 2WH, 2LH, 4E squared. I don't think we get into lateral area on the exam. But surface area, you need to know. Okay, so the 2LW plus 2WH plus 2LH and then 6E squared. We got the pyramid thing, square pyramid, that's what it's called. The square pyramid. Remember, you got a square, that's a B squared. And then remember, that's the slant height. It's not the actual height of the pyramid. It's the distance from the base of the pyramid to the top along a face. Okay, so that's your slant height. Not quite the same thing as the true height of the pyramid. There's your 4 times a half BH plus B squared, or I might say 2BH plus B squared is the way I looked at it. So again, mainly just know those formulas. Again, I think we're capable of plugging in the numbers as long as we know the formula. Okay, so a lot of memorization to brush up on there. Cylinders and spheres. Cylinders and spheres. You got cylinder there on page 258, the 2 pi RH plus 2 pi r squared. Again, the lateral area would be just 2 pi RH, but I don't think we do anything with lateral surface area on the exam. So yeah, 2 pi RH plus 2 pi r squared. Again, the 2 pi RH is the length of the rectangle in the net, and the 2 pi r squared is 2 pi r squares, are 2 areas of circles for the top and bottom bases. The sphere, remember, is 4 pi r squared. 4 pi r squared. That one's a little harder to remember because there's not really a net you can draw for a sphere, of course. Then we talked about volume, page 263. Page 263, volume. And again, that's how many cubic units can fit inside the three-dimensional figure. V equals LWH, that's your basic rectangular prism, your box. E cubed, remember, is your cube. Your cylinder, pi r squared h. Again, your circle base times your height. So in general, remember, base times height is kind of the basic. Area of base times height is your equation for volume. Questions on any of those? Or as we're looking at it, you're like, yeah, I remember this now. It's been a while. Okay, been, what, 7 weeks? 6 weeks since we talked about this? We didn't talk about that. Okay, page 268, 4 formulas. Pyramid, a third b squared h for the square pyramid, 1/3 b squared h. The cone is also a third, but it's a third pi r squared h. A third pi r squared h. Your volume of the cone. Remember, the 1/3 is something to remember for anything that comes to a point. Remember the 1/3. Spheres, 4/3 pi r cubed. It's not a good way to remember, it's just weird. 4/3 pi r cubed. And I think that was it as far as chapter 6. Any of those formulas, as we were looking at them, you're like, I don't remember that. Any of those you want to practice with? We are going to drill formulas here in just a moment, but any questions on working with any of those formulas? And again, if you can use that 22/7 to your advantage on a pi, save you a whole bunch of time, right? So watch for those 7s. Questions on that?
I just keep getting diameter and chord.
Yeah. Well, basically, diameter's special, right? It goes through the center. Chord is just a boring term for anything that starts and ends on the circle. So, all right. Well, tell you what, let's go and drill some formulas here. There's some other random cards mixed in here. Sorry about that, but we're going to work backwards through here.
Sphere.
Which one? Obviously,
Volume.
volume of a sphere. The V's not on here, so volume of a sphere, right? Because it's got the cube. That's how we know, and that's a good observation. You see cubed, it's got to be volume because, hello, so cubic units, 4/3 pi r cubed. You know it's got to be either a pyramid or a cone, right? And the fact that there's pi tells you it has to be a cone.
Yeah,
Cone.
what?
Because pi is involved with circles, right? So the one with the circular base is the cone. So you know it's the 1/3 means pyramid or cone. It comes to a point. The pi tells you it's got to be cone. So 1/3 pi r squared h. Of course, you also might recognize the pi r squared h as being your cylinder volume. So volume of a cylinder. Also, there's cubic units here. 2 of the units are on the r. 1 more is in the h. So it's 1, 2, 3. There's your cube. If you want to think of it that way, that's getting into a little bit of deep algebra there, but anyway.
That's the pyramid?
That's the pyramid. So it's also the 1/3, but you got a squared base, b squared, and then you got the height. Notice the true height there as well, by the way.
That's the cylinder.
That's your cylinder volume, right?
Volume of a cube.
Volume of a cube, there's only one dimension given. That's the same all the way around.
Volume of a rectangular prism.
Rectangular prism, box, but rectangular prism is the technical name for it. Good.
Area of a circle? I mean, no.
Sphere surface area.
Yeah,
Right, the surface area of the
Oh.
sphere is the 4
Yeah.
pi r squared.
Is that the cylinder surface?
That's the cylinder surface area. You've got 2 circles at the top and bottom, and then there's the wraparound on the outside. Yeah, I know, it's been a while, right? So, hey, if nothing else we're learning from this review, we can just study those formulas tonight, make sure we've got them. Maybe copy them out, or make little flashcards for yourself and drill them. This is a lateral surface area, which we're not going to get into. That's just the first part of the other. It takes off the top and bottom circles. There's your lateral surface area of the cylinder.
I know it's a volume.
We've got a base, and we've got 4 triangles.
Is that the trapezoid?
What would have a base, a square, and 4 triangles?
A triangle. No.
A square pyramid. square base, and then 4 triangles that all come together at the top, right? So this would be your square pyramid. Again, if you can kind of read between the lines, you know a half BH is triangle, right? So 4 triangles plus b squared, side squared, if you will, is your square base. So there's some ways you can kind of read into this. This is a lateral surface area. Cube, okay. Also lateral surface area.
Is it rectangle?
That's the rectangular prism. It just took off the 2LW, which would be the top and bottom of the box.
Surface area.
Surface area of cube.
Surface area of rectangular prism.
Good, surface area of rectangular prism. Here's some pictures, I believe.
Torus. Sphere. Cone. Cylinder.
Cylinder. This one's interesting.
Pyramid?
It's a pyramid, but it's specifically a tetrahedron because it's triangles all over. It's not a square pyramid, it's a triangular pyramid or a tetrahedron, 4 triangles.
Square pyramid.
That's the square pyramid.
Triangular prism.
Prism, right? We've got the front and back bases are the same, and it's a triangle, so triangular prism. Cube. Rectangular prism. We have rectangles on the front and back, and then same surface area or cross section throughout.
Area of a circle.
Area of a circle, yeah, that's one of the easy ones there.
Circumference.
Circumference of a circle. Let's see, we're going to skip that one. Skip that one, skip that one. Okay, here we go.
Surface area of a trapezoid.
Not surface area.
Volume of a trapezoid.
Area of a
Area of a trapezoid. Remember, a trapezoid is a plane figure. There is no surface area to it, it's just a single surface. It's just area of trapezoid.
Area of a triangle.
Area of a triangle.
Area of a parallelogram.
Or area of a rectangle. Rectangle, parallelogram, same thing.
Area of a square.
Area of a square. Okay, so it's kind of the rundown on the formulas.
Wow.
All right, if nothing else, it showed us where we stand, right? I'll tell you what, let's do something here. Let me do the back sides of some of these surface area things. Because that's where things started, the wheels started to come off the wagon here. Let's see if we can remember what the surface area of a rectangular prism would be, Lana.
Was it the 2 pi? Wait, no, that's.
Picturing a rectangular prism, picturing it helps. Picturing a box. Can you help her, Josh? There's a length and a width.
Yeah.
There's a width and a height. There's a length and a height. But there's 2 of each kind. Plus 2W. There you go. 2LW plus 2WH plus 2LH. And those could be in any order, right? Those terms could be commutative since addition's being used there. What about the surface area of a cube?
6e.
Good, 6e squared. Glenn knows these. This would be, remember, minus the 2LW part. That's also lateral. Okay, here we go. Square pyramid.
Oh, 2 pi. Not 2 pi. 2BH plus B squared.
Good, 2BH, or 4 times a half BH, 4 triangles, plus the B squared base. Okay, so 4 times a half BH or 2BH plus B squared. That's a lateral surface area, a surface area of cylinder.
That's 2 pi r h plus 2 pi r squared.
Good, 2 pi r h plus 2 pi r squared. Surface area of a sphere.
4 pi r squared?
4 pi r squared. It's equivalent to if you were to take 1, 2, 3, 4 cross sections. Like if you imagine looking at the top of a ball and cutting it in the shape of an asterisk. That's 1, 2, 3, 4 cross sections. If you added the 4 cross sectional areas together, it would equal the surface area of the entire sphere. So 4 pi r squared. Volume of the rectangular prism. That's just LWH, right? All 3 dimensions. E cubed is your cubes, just all, it's length, width, height again, but they're all the same, we just call them E. Volume of the cylinder. Area of the base times height. What's the area of a circle?
4 pi r.
What's the area of a circle? Just plain circle.
Pi r
squared, H.
Oh.
Right, so pi r squared H, your volume of the cylinder. Now a pyramid.
I know it's going to be a 1/3.
It's got a 1/3. There's a square, which would be, that's just a square. Side squared or b squared,
Yeah.
h.
Yeah.
So a third b squared h. Okay, what about the cone?
1/3 pi r squared.
Good, you've got the circular base, that's pi r squared, h, but it's a third of that, so a third pi r squared h for the cone, so little ways to remember. And then the fun one, volume of a
4/3 pi r cubed.
4/3 pi r cubed, because it's volume, right? So study tonight. There is no homework tonight other than study and be ready. Study and be ready. That is your only homework tonight. And it's chapter 6, chapter 8, chapter 9. I feel like chapter 8, probabilities, mean, median, mode, should be good. Chapter 9 was graphing. I feel like we're pretty good at the graphing. Chapter 6 is probably where we need to spend the time now, isn't it?
I usually don't study, but this time I'm
There's enough formulas you need to study. All right. Have a good day, Scott.